All right, we are recording. I'll get back to MATLAB in a sec. So I do have some new gifts for all of you if you go to Canvas. So yeah, so when you look, there should be two things. There should be, well, there's actually more than two things there. But one of them is two alternate ways to do the same thing. So there is this, let me get down here. So this one here, the con, noi, GUI, mlap, and an installer. Theoretically, this one should do. This is the underlying MATLAB file. This is a MATLAB application installer. So if I wasn't sure if this one was going to work or not, so I just made a package to install it if you needed to. In theory, you should only have to use this one. So this is kind of more of a safety feature. And then there is this new PowerPoint.
Is it supposed to look like this?
What's that?
It's supposed to look like this.
Yes, we'll get it. When you run it, it should start showing something. But
We're listening to make a gray box function. Which one did you run?
We might have to write that real quick. I thought I had stuck that in the package, but I guess it didn't. Make the gray box thing is a real simple application, so we can do it quite easily. Yeah, you could, if you want to, it might be in the installer. We'll see how smart they were. Thank you.
Oh yeah. Go to wrap it up.
In theory, the installer should wrap it. The only disadvantage to that one is it'll be hidden from you what the code looks like. But anyway, we'll talk through the PowerPoints first, and then we'll worry about the rest of the stuff. All right. So let's first talk through noise, artifacts, distortion, accuracy, things of this sort. So I'm presuming most of you have had some amount of stats already. Yes? Okay, so let me ask you some basic questions. We'll see if we understand the concepts we need here. So what do we mean by a random variable?
Anything that we don't know the outcome for happens.
Okay. What do we know about random variables?
Well, we can know potentially a probability distribution.
Okay, so that's a probability distribution would be kind of important to know. Right now, there are parameters. How likely is it we know the probability distribution?
Depends on what it is. If it's simple, we probably know, but if it's more complicated,
So even sometimes with complicated ones, we often do know, right? We'll get into some things how you can kind of look at some areas, but noise and random variables come from a source. So there's going to be certain modeling assumptions about that source. What do we know about it? And this is one of the reasons why we're going to start looking at physics next week of things. Because if we understand the process where things come by, we know where noise can enter in. Knowing where noise can enter in, we'll get some information about them. Right? So it's, if we know something is talking about arrival times, there's a high likelihood a Poisson distribution is describing it. And if we know it has to do with scattering through a uniform medium, it's highly likely it's going to be Gaussian. Right? So there's some of these kind of basic distributions that we can say some properties about, right? If we're looking at events spread over time occurring that have certain decay properties, it's exponential, right? So there's a lot of different distributions that we can look at. What are the basic properties? What is the thing going on? But you can only figure that out if you know where the noise is entering in and what the underlying physics of the situation is. This is why it's so important for us, because the noise is going to become very significant to us. Now, if I know the distribution, do I know everything I need?
How many times a period, maybe?
I'm making kind of a simplified assumption. So if I tell you, this is a Gaussian distribution, is that all you need to know? What else do you need?
The parameters, something else.
Yeah, now I need the parameters too. So understanding what those parameters and how they're going to influence it. Like we often think, well, you said you knew the distribution, right? But you'll understand in the physics, you'll get the model, and you might understand how you might be able to figure out what those parameters are, but those parameters are going to depend on operating conditions. And so operating conditions will change even for the same device. As a device ages, it will change. Right? So you can't, from modeling, say in advance what those parameters are. You might understand a range to them, but you actually have to measure those. Right? And that's another really important condition that's on here. Right? If I know a Gaussian, how many parameters do I need? Why only two?
It's really well behaved.
Okay, why? Well, what about it is so nicely behaved?
Shape is very constant. It's all very proportional.
Okay, and we talked a little bit about this when we talked about last time the Fourier transform, that Gaussian distribution is kind of a fixed point, and it's got this nice property of being second order stationary. And that second order tells you how many moments until it goes flat. It goes to zero. Then anything after it, the moments will keep generating zero. Right? So you only have two non-zero moments that drop out from its calculus, right? And that has to do with the actual equation for the way the distribution is generated. That gives you kind of the ideal shape for a curve, right? In at least the sense that it has this kind of nice properties. Are there ones where you have more parameters than two?
Like distributions?
Yeah.
Yeah.
All right. How about less?
Isn't like standard normal one?
So standard normal is, you get two technically,
Okay.
right? You have the mean and the variance,
You found that.
right?
Is it Poisson?
Poisson, right? It has lambda, its rate parameter, and lambda will generate the mean. The variance is also dependent on. So we just say you can describe them because the mean and the variance for Poisson are related to each other. So you can get less. Are there any other cases where you get less? And that one's nice in that there's a single parameter that's going to describe, both your first and your second moments. Can I ever get less than 2 moments?
Uniform. Would that have uniform distribution?
So you actually can calculate more moments for that one, right? And so think about how you have to calculate, right? You have to calculate an integral. So what's going to cause an integral to blow up? Will it blow up on a finite size space? No. So what's going to cause it to blow up?
Extending.
Yeah, as you go out to infinity, it doesn't drop off to zero fast enough. This is the condition you have to worry about. This is often referred to as having a heavy tail or a fat tail. All right, so heavy tail distributions, when you attempt to integrate them, they're going to have too much power, too much probability of rare events. Are there any common distributions that have that property?
Second one for a motion.
Yeah. Right, chi-squared also. Right, there's a number of these. So there's actually a bunch of ones that actually go in, and some of these actually relate to medical imaging situations, right, where you just literally cannot calculate those moments. Right? It doesn't mean you can't describe that function, but it does tell you it's not going to be nicely behaved. When you get those ones where you can't calculate the moments, you're going to end up with situations that you'll have basically lots of spikiness. And the more spikes you see, in some sense, the worse it is. Because spikes are telling you, when you look at a running average of them and stuff, if you still see spikes, that means there was a very, very large event. And that's outside of it. If you take a look at chi-square variables and you do a running average, just keep adding the new one in and update the average, you'll see it'll, like most distributions, it'll smooth down law of large numbers, and then it'll just spike up. And those spikes happen too frequently, these really, really rare events, so it never really settles down, which tells you the law of large numbers doesn't apply to them. It's not going to nicely converge. It will be moving kind of towards it, and then it'll get thrown off. So a lot of good things we rely on become very ugly under those cases. So you just have to be very careful when you hit them. Does that make sense? Just this is hopefully bringing up some properties you're familiar with. Now, a lot of these we'll take a look at and just see from the model. If we know it's one where we can calculate moments, i.e. it's integrable, right, then we're feeling pretty happy. If it's second order, then we're going to be really happy. And if it's not, you can usually find this by seeing, can you calculate that third moment, right? So you'll see third and fourth moments like kurtosis and things like this are going to be calculated. Skewness, right? Kurtosis is fourth and skewness is third, right? If you see a distribution that's tilted one way or the other, you're not dealing with a nice symmetric distribution, then you're going to have a third moment, because it's skewed, and that third moment is the skewness one, right? If you're looking at the fourth moment, kurtosis, that has to deal with how much is inside versus outside, how heavy is the tail versus the center, right? The spread of them. So fatter tail distributions, not getting as bad as the ones that completely blow up and you can't calculate, but there are fat tail distributions that still you can integrate, or heavier tail, I should say. And you'll see that with your kurtosis number, right? Whether it's positive or negative, it tells you how much it's skewed towards the center versus the outside. With the Gaussian being 0. Okay, so that's kind of what you're getting with those random variables. What's the importance of independence? What do we mean by independence?
Yeah, from one has no relation with another.
No relation in what sense?
They're not
Because there's careful, right? We can't say that there's no relation,
true.
right? Why? They have the same distribution, right? They're coming from, I mean, if you're dealing with, standardly what we'll have for a lot of independence is what we call IID, right? Independent, identically distributed variables. And that's usually the ones we're getting. You don't notice they have, here's a uniform one, and the next one coming down the line is Cauchy, right? So typically you're going to get one within a distribution area. But the independence feature within that distribution is still really crucial, right? So what does independence give us?
does that mean we can operate on things linearly?
So it does give us a lot of that nice kind of properties that come down, because what can you say about the probability of knowing one event given the other? And this, yeah, right? That's the part that's really important. And that, you know, just because you've sampled once doesn't mean you can tell me what the next one's going to be. It's going to follow the same type of distribution for picking it, but you can't actually say what that particular choice is going to be. And therefore, when you calculate things like expectations, that independence becomes really important, right? This is something we want for our noise. It's not guaranteed in all cases. When can I get something that's not going to be independent? Do you think of a case where that can happen? So what would have to happen for that to happen, right? So part of the reason why is because you will encounter these things, right? And you'll get some areas when you look at the correlations. Oh my gosh, these things correlate. What the heck do I do now, right? So I want to be able to uncorrelate the variables. So we have to have some idea how they get correlated. So this is why you want to think, when can that go? So this is the difference between a mathematician and an engineer. So I'm asking you to think about these different in some sense. I want you to think about it like an engineer, right? You know, you can look at the standard things of calculate the expectation, and the joint expectation is 0 and stuff like that, right? So that's ooh, lovely, right? But when does it happen that that's not? So what would you need in order for two things not to be out?
They kind of have to have a common event.
Okay, so they have to have something common that's somehow filtering down to them. So that means there'd have to be a function. In our case, these are transfer functions. So the noise would have to be an input to a system, and I'd have to have two outs. And that system would have to have some common variables. So it can distort it, it can combine it with some other things to make them look a little bit different, but they're relying on a common source of information. Is there a way I can get rid of that then?
Only if you can find where it's coming from.
Yeah, so I have to, at this point, be able to model the system and say, okay, what does that system look like? I can figure out what that transfer function is for the noise, and I've got two outputs. So I can then take a look, well, what could it be? Right, that noise is coming in and it's related, so there has to be something that's common between them. So for instance, like on a plane, I might have something where, you know, noise excitation outside, it's based on the turbulence in the air, that could deform the plane's body, number one, causing one type of noise, and it could also, as it comes down, there's a correlation of the data as it moves down the plane, right? So you get the planes flexing and you get the movement of the pressure wave down the plane as the plane is flying. Those can look like two separate signals. And then you just say, oh, how do I now step back and model to the atmospheric noise? So we call that one when they're correlated like that, colored noise. Because usually since it goes through some type of a transfer function, transfer functions are going to have a Fourier transform that's not going to be flat in general. It's going to have something, so there'll be a drop off. So certain frequencies are going to get emphasized differently. Does that make sense? Some are going to get, you know, knocked down, usually as you go towards higher frequencies. Some other ones are going to get peaked, depending on whether it's a first, second, whatever order system. Right? But that means since certain frequencies are emphasized and other ones removed, what happens if I take light and some of the light waves I keep and some of them I throw away? What do you end up with? Colored light. So if you hear about colored noise, right, what that's telling you is it went through a transfer function and certain frequencies were preserved and some were not. If you hear about white noise, what does that tell you?
It's all,
All frequencies equal, right? So that's typically what you get with that type of, you know, IID Gaussian, right? Zero mean, unit covariance, white noise will give you that nice distribution all the way across, right? As you pump that through a system, you're going to get colored noise. Typically, what you're going to get is pink noise. Right? Did you ever hear pink noise? So what's pink noise?
Lower frequencies.
What is pink? It's red and white. So you got some amount of frequency all across the board, right? But it's heavier towards the red end of the spectrum. Where's red? On your frequency range. Is it high or low frequency? Low. Right? As you go, the colors as you move towards blue and purple and ultraviolet, that's getting higher energy, higher frequency. Right? So red is slow. So we use red on our rainbow pattern to just say the lows. And if you think about a typical transfer function, what do they look like? They tend to kill the high frequencies. They can't pass them. Because passive systems in the universe, most things are low pass filters. The vast majority of anything you're going to deal with as a real system that's kind of out there is probably going to be a low pass filter. Right? This is why we make the assumption noise is high frequency and your signal is low, because your signal is coming from generating systems, and they tend to be low pass filters. Right? You ever try to hear somebody's voice from a great distance off? What type of voices do you hear farther?
Higher, right? Yeah, higher.
So think about, like, anybody ever see like those Ricola cough commercials?
Uh-huh.
What instrument do they use?
They use like those massive,
Super. And what type of sounds do they make?
so low.
Why? Because they travel a great distance,
That's interesting.
right? It's the easy way to do it. Because mass is a low pass filter. So therefore, low frequency waves are going to move easier through any physical medium. Okay? That's why, like, why does your car, when you go faster and faster, why does it smooth out on the freeway? If you drive really slow, it's really bouncy. As you go faster, it gets smoother, right? Why? Your car is a mass on top of a shock absorber to a tire. That's a spring mass system. So you're dealing with a vibrating mass. Your car is pretty heavy. The inputs are your tires being hit. The faster you go, the frequency increases. So when you go faster and faster, faster, can the mass move to that? Can it respond to it? No. How about a low frequency one? A hard, slow shove? Yeah, of course you can. Right? That's why when you go on the freeway for longer, it smooths out.
Yeah.
It has to smooth out. Right? But that's true with almost every signal you have to deal with. They're gonna, in general, in the universe, it tends to be a very passive system, right? It dissipates energy, so it's gonna tend to move you towards those low frequencies. So low frequency voices go farther, right? Because it's just the nature of the beast. Those ones don't get attenuated by the mass of the system as much, whereas high frequency ones do. It'll even somewhat change the way things sound at a distance. Your voice will sound deeper the further away it is, even if you're not moving. It's not a Doppler effect, right? Because your voice is a range of frequencies, and the higher frequencies damp off. Right? So you're just going to sound deeper further on. Right? On top of it, when you go through, like, anybody ever notice the difference between how some of these voice sounds on a phone versus not? What happens to a voice on a phone? They're different, right? Yeah. Why are they different and how? Because it relates to us, because we also have to transfer signals,
I
right?
know that like when you're speaking, the sound like travels through your body. And so I think what I think is that my voice sounds lower than it does on the phone. I don't know if that's what you're
So that's
what
different
you're getting at.
from you to somebody else, right? So if you if you're hearing your own voice here and somebody records it and you listen to it, the recording back, okay? Your voice will sound very, very different.
Yeah.
I'm not asking that one. Imagine I called you on a phone
Right.
and you compared my voice in person to my voice on a phone. They're different.
Yeah.
How are they different?
Is it higher pitched?
Where?
Like you're hearing it higher pitched than it actually is?
Believe it or not, it's the opposite.
The opposite? Okay.
It's lower pitched, right? And it's lower pitched because they band limit your signal. Right? On your phone, they actually filter it because can the wire transmit an infinite range of frequencies? What's going to happen to those really high frequencies? Because they're going to want to digitize this for efficiency, right? So if you're going to digitize something and you have a really wide range of frequencies, what happens? Those really high frequencies become noise. They're not all the airs in there. The signal gets weaker and weaker out there. It's just not good. So they just say, let me just throw that all away to remove cracks and popple and everything else. So they limit it. The standard rule on a phone is sampling around 4K. Human voices are way the heck above that. That hits into the mid-range, right? So this affects women's voices much more than it does men's because their voices are higher pitched and more of their energy is going to get filtered out. Right? But the same thing's going to happen to us. We have to measure our signals and transmit them. So effectively, to remove noise, we're often going to have to low-pass filter them. Okay? So this becomes kind of one of those important areas. We want to think about the bandwidth of the signal we're able to transmit down our lines. On top of it, there is going to be an effect of all of our signals passing through, any system that's out there. Some of it we want. That effect is what we're trying to measure. Some of it's going to be unwanted side effects. In ultrasound, there's some examples where it kind of even flips. So in ultrasound, for instance, one of the big noise types is speckle. We'll talk about this when we get to ultrasound more. Speckle is usually considered bad, noisy. It makes it look grainy and splotchy and everything. But it turns out that the speckle can actually also tell us things about movements and shapes below the wavelength size. So it turns out that it's noise that has a source and we can go back on it. This is that, speckle and some of these other variations are the basis of doing some of the areas to find out blood flow rates and all kinds of other stuff. Right? So sometimes the noise is useful to you too. Right? I just mention these because a lot of times people just get a very simplistic view. Noise, filter, gone. Right? Not always true. Right? And understand where it came from, what it means. We'll decide when do you want to get rid of it, when do you want to keep it. And no system is just one system. It's always cascades. Right? So knowing what each cascade does will tell you how to tune those to be able to get the answer that you want. Right? All right, we feel good with that? Okay, real quick. Does everybody remember what SNR is? What's SNR? Signal to noise ratio. So I give you two different types there, amplitude and power. Right? Key difference. What's amplitude, SNR, and what is power? And why do I want each?
Typically, the amplitudes we measure are root power quantities, so you have squares.
Yes. Yeah. So the relation is going to be a square between the two. Right? Power is usually proportional to energy, right? Energy over time. Right? Energy is always a square. So it's an easy way to remember. Whenever you hit the power, it's a square, which is why when you go to dB, you get 20 versus 10, right? That's that square gives you the 2 difference. Why even deal with amplitude?
They're in linear space, they're not in a square space, so you can add them straight up.
And a lot of times it's really straightforward from some of the information. Okay? So for instance, consider I was dealing with a system that has Poisson variables, right? Or actually, it could be Gaussian or whatever. In general, my signal tends to be proportional to the mean. Right? Usually the mean is typically what you're looking for in most cases when you filter out the rest of the junk. Right? So you filter towards the mean, that tells you what you were looking for. So the noise is going to be related your standard deviation. Right? Variance would be power related, standard deviation is amplitude. So I can in general kind of approximate, hey, if I know what the random variable is, my SNR is basically, at least in amplitude land, going to be mean over variance, or mean over standard deviation, I should say. Right? So it's kind of a quick way I can look at something, just down and dirty, get an idea how good is my signal. Okay? So that's just real quick look at it, right? Particularly when noise is coming in, what's going on. Now, you know, there are a lot more sophisticated ways to do it, but that gets you a really quick ballpark, and it's a pretty good approximation in most cases. All right. This stuff is pretty familiar with all of us. Let me talk in particular on some of this just to give you an idea on some particular. The second one here is for X-ray reconstruction, and this is just some pictures of them. It might be better on your screens. Unfortunately, the projector often washes things out. But I want you to understand what's being shown here. Okay? So if you look here, see how you have right here, right, milliamp seconds that's going on. So this is telling you some information basically about how much current has flowed through, right? You know, because it's telling you basically, you know, I was putting a particular current for a particular period of time. That's going to tell you the current is going to be proportional, this is in an X-ray, to basically the filament wire. So that's going to predict how many X-rays you get. The more you increase the current, the more X-rays. And then you run it for a period of time. So milliamp seconds is basically saying proportional to how many X-rays you had, which means it's proportional to your signal strength. You are measuring those X-rays. How many did I have before? How many do I have after? That gives me my signal. So this is telling you as I up the amount, now this increases dose too. So the higher you go up here, the more radiation, because otherwise we're going to say, well, heck, rank that thing up to the high heavens. And that's lovely, but then you fry somebody, right? So it's a trade-off, right? So the question now is, this is when it becomes an engineering problem. Engineering is all about trade-offs. It's the waterbed effect, right? You go too small, it doesn't do you any good. You go too high, you hit another, in this case, you kill somebody or cause radiation problems that might have to get dealt with, things of that sort. So there's going to be a good trade-off between these two ends, right? And when do we hit that? So that's what this is looking at. The columns here are two different ways to reconstruct. This one, FBP, is filtered back projection. Filtered back projection is just a flat, it's a closed form technique. You follow this area, it just is what it is, right? And you get your answer. There are a little bit of differences you can do because you can do different filters, right? For the filter back projection, we're saying that, you know, the standard is RAM lac, but it's kind of high noise, so there's a couple alternatives that are out there. But essentially, it is what it is. You get what you get. You know, there's not a lot of tuning or altering you do, but it's fast. It's fast. It's got artifacts, right? These ones are actually iterative reconstructions. Anybody ever had like a course talking about POX or something of that sort? Projection on convex sets, or ART, algebraic reconstruction technique. In the medical field, they like to call it ART, particularly X-ray area. But anyway, so this is using that. That technique, there is no final solution. It's all getting closer to it. Now, you might say, well, why would I want to do that? It's slower in that sense, right? To get a final answer, because you have to just keep going, and you never really get the answer. You get closer and closer to the reality. But the advantage is that there's a lot of dials you can twist that allow you to do things like, oh, if I switch it this way, I can reject noise a little. I can emphasize the high-end frequency range. I can emphasize, right? So there's ways I can tune a POX or, you know, any other iterative technique. There's other ones as well, right? To be able to go into it. So if you notice generally between these two, notice how it is not quite as strong on the graininess of these, right? When you come over here. This one took more time, but you're able to get a better answer. Now you can actually take the output of this and shove it into this. So there are ways you can kind of combine. But this one in the end will take more time, more compute resources, give you a slightly better solution. And that's what they're kind of showing through. So you can see here, this is the contrast detail phantom we talked about before. Right? So remember, the larger ones correspond to how it's responding to lower frequencies. As you get smaller objects, it's kind of measuring how it responds to higher frequencies. And then it goes through different densities of them. Right? So on the top, you have the most dense objects, so they're going to be the easiest to do, and they drop the contrast down. And the idea is you're trying to look through these to see where it is, because it gives you an idea of what the response of the system is to frequency and signal strength. And you can see as it goes, as I go up to it, you're able to see a lot more features that are in there, and you can get the shape more precisely. Right? So you can see that type of behavior, and if you watch, it gets kind of hard here, even on the good one. Like, that's probably a dot, seems to be following the pattern, right? It's even harder to tell here, but it's still maybe there. It's on the edge, it's a little bit thick for it to be maybe just straight noise, but it's kind of getting questionable. It sure as heck is, I don't think you can tell very much on this one, right? But you can start seeing that next line coming in line here as I have the dose that's coming in. So this is one of those important trade-offs, right? Our signal to noise ratio, right? This is upping the signal strength in essence. But there are other things that will help us do it, right? This is another transfer function that's going to be coming in, right? And they're going to have different properties. So that's what we're going to want to emphasize. All right, do we feel comfortable with at least this from this example area? So I'm going to have you write both of these different type of algorithms, and we'll take a look at how we can tune them and see how it affects the noise. So that's, after we've talked about the physics of it, we'll move to where you actually do the reconstruction and see how they operate.
Between the two of the techniques, which one's usually the go-to? Does it just depend on resources?
It's heavy to it. So as you look at older machines, they're almost all FPP. Just because resource-wise it was, cheaper, easier stuff. There's still a lot of people in X-ray land who that's what they care about, right? As you try to lower the dose, right, and computing resources go up, it's more and more moving to the iterative.
Okay.
I'd say in the last 15 years, things have been moving much more heavily towards the iterative because we're trying to lower the dose.
Yeah. Okay, that makes sense.
But yeah, it's a good question. You'll find people today who are still die hard, right? There are almost, that kind of joke about the big Indian, little Indian, or religious wars, or whatever you want to call that. There are some serious opinions where people get like bent out of shape over these. I find them both techniques. And I encourage you, don't get too hung up. Even if you use one all the time and you really love it, realize there are multiple techniques because none is perfect. So what you want to do is have a good bag of tricks. And even if you think yours is the best, sometimes you might want to just steal a couple things from the other one by integrating it in, as a pre or a post filter. This one just introduces the same idea, but you can look on these and see this is for contrast. We drop the contrast on the signal. So the noise is consistent throughout it, but it changes the signal to noise ratio by the density of those. And these are profiles. So the line that's drawn through here, that cut section, if you were to take the values of these right there between 0 and 1, and if you were to plot those, this is what it looks like. Now what's kind of interesting, when you look at these cut profiles, this gives you an idea of how accurate it really is. So to my eye, I can see that box really easily, right? But does it give me, now I would ideally like to see low line up rectangular, right? That's what I want to see. That is what it actually is. Now, you can see the low ones here. It'd be better if they actually have them on the bottom in some sense under each one, but it might be hard to see the noise. Anyway, if you looked at this, right, you could say, oh, okay, this is, right, coming through is that a rectangle where you can kind of see the high point and the low
Yeah.
point? But notice that there's kind of a dip as you're coming into it. There's a little bit, this will actually happen, we'll talk about hardening in some other areas, but there often is an area where it gets a little darker, a little bit brighter inside, there's an overshoot. On a lot of these ones, I'll show you a picture later that shows us even more. So there's a lot of this type of effect near edges that happen with objects. It's in most physical systems. I can still see the rectangular or square area there, but notice it's getting harder and harder. See, the edges are killed pretty badly. How can I find them really well? All right? So that becomes kind of an issue as well. And you can see as the signal to noise ratio goes down, it's hard to see on here because I think the projector's not, but if you downloaded the PDF, like if I look on mine on the screen, which does a better job of showing the stuff, I can still make the rectangle out on the top one. It's not great, but I can make it out. But I defy you when you look at that profile line going through there to try to consistently find that rectangle edge. It's just not particularly nice. So this becomes kind of an issue, but this really is the standard because most people will look at it. Your brain is really efficient and you have trained yourself to look for shapes. So you are really good at picking those shapes out. The problem is when you want to actually make quantitative assessments about what's going on, you need to know what those materials are. Well, to tell exactly what that material is, that particular material here is not just what is the shape, but what's in it. And what the signal response is to a particular dose is going to be proportional to the atomic number. That's going to tell you what the material is, right? So higher atomic number tends to be, associated with, metals, things of that sort. Bone has an effective Z higher. So they call these units that are in their Hounsfield units. So it's affected by atomic number and density. Right? So the more I move towards that dense or higher atomic number area, I'm dealing with fillings or the enamel on your tooth is of your naturally occurring substance in your body. It's about as dense as you're going to get. So usually the strongest artifacts related to dense objects are in your mouth. But it's going to be different to them, and knowing what it is really important. If I'm dealing with, like, say, somebody's looking for hip cancer, bone cancer will often weaken the bones. So one of the more important areas is actually making sure that those bones don't break after it, because I hit it with radiation. We want to make sure that once we've killed the cancer, we don't end up with somebody who's highly likely to get a broken bone. A lot of those bone cancer occurs in older patients. You get a hip fracture and you're 80, I just signed your death warrant with that one, right? The likelihood of you making it is low. Right? So, and it turns out there are ways we can handle it, but in order to tell how dense your bones are, I need an accurate number there, right? And this makes it very difficult. So being able to tease out the right area and tell where the edge is lets me find the margins of the cancer, lets me find the margins of whatever condition I'm dealing with, lets me assess the density, a lot of important features. So being able to get to those numbers accurately is very, very important. So that's why we're going to sweat this, right? Because it really matters to us. Okay, here are some artifacts. So artifacts are things that appear inside an image, but they're not there. They're not real. So just think of it. Anytime you hear the word artifact, it's fake, right? This is something for whatever reason. It could be the physics of the system. It could be the sensor has a thing. It could be your reconstruction algorithm has a thing. It's going to generate some falsehood, right? And that falsehood would look like something, but it isn't. So for instance, let me just start over here. See the ring artifact? Anybody have an idea where these ring artifacts might come from?
Filter back propagation.
Yeah.
Rotate around.
FBP. Yeah, it's actually, so I have to take an image of something in 3D, I take images from all kinds of different directions, right? That's the center of rotation. Is there any way I can get rid of this? I can't totally get rid of it, but I can actually mitigate that pretty strongly. What? What's that?
Using art.
So art will actually help you with that, but there's actually even an easier way you can do this with FBP too. Right, so in general, what most people do is they center and they pick a center pixel that you're gonna rotate about, and you rotate around it. This is called the isocenter, right? If I put that isocenter at the conjunction of multiple pixels, so it's not actually on any one. I don't want it to be on a corner between them. I don't want it to be in the center. I want it to be off center. As you rotate, it'll wobble. The wobble is going to cause noise cancellation, and the rings cancel each other out. So if instead of putting it on a corner or in dead center, you put it like halfway between the two, it wobbles and most of those rings go away. It's a stupidly simple idea, but we're so often set up logically to, I'm going to set it at this nice, perfect little, let me align it great. It turns out if you don't align it that great, you actually can improve some things. All right? So you deliberately defuzz it so that the rings cancel out with each other. All right? Now, it will turn out that other types of techniques will also help you to do this, because if you're not pushing back in a ring fashion, you're not going to get as many rings. See that beam hardening? See how this looks really dense, right? In this case, lighter is going to be denser. We usually invert X-ray images. That's on the edge of a thing. Notice how that edge looks like it's super dense. If you actually look at a lot of X-ray images, you'll get this thing. The skin, the outer thing of particular surfaces, look really, really dense. It's not true, but it's an edge effect when you come in, because there's these Gibbs phenomena rings. It's going to cause things to appear to go on. Plus, you get ones that kind of hit on the very edge and skin, and some go through and some don't. Again, ones that come really close inside the voxel but don't actually hit will go through unattenuated, and it'll make those outer ones look brighter. Okay? So, this type of an effect is common on that, and so it's called beam hardening or a bunch of different ones. But it makes the skin of the object look really heavy. So we have to correct those. It's not true. Right? You don't have super hard skin there. It's just an effect of the measurement system and some of the problems with it. Take a look on the top. What's going on there? Can you see what's causing the problem? I mean, obviously the problem is those streaks, right? So there's no, inside your mouth, there really is not like this halo of streaks between left and right side. So what's going on in that spot?
Those fillings or metal objects.
Yeah.
That's
That's a filling right there. You can see it between two teeth. And what happens, it's so dense, it strongly interacts. And we'll talk about how they interact, but whenever you interact, it's going to bend things. Right? And when you hit really dense objects, it's going to have a very profound effect. And then we're spreading things back in FBP. It causes streaks because that really dense object is going to affect strongly, right? It's going to want to be a really big spike, but we spread things backwards. And noise in our measurements mean we can't perfectly reconstruct anymore. So therefore, that strong spike is going to be spread to some of the nearby areas. Unavoidable for that. Now, art will not have this problem, right? Or more correct, I can correct it, right? So it tends to avoid that because I can emphasize some of the other directions that don't go through it, and I can force those ones back down again, right? Which will force that energy back in there and push it up. But different ones, different things, right? All right, you can see it also here. This one is not in that same area just because it's dense. If you look at your image, it's really hard to see here. There's kind of like these streaks coming off the edge of the circle. Right? So edges of things, if you take a look at bones, there's often like little spikes inside and things like that. Like your bone is not perfectly smooth. Right? So there are some areas where there's kind of like points. Where those points are sticking out, you'll get these streak artifacts oftentimes. Right? So that's kind of those type of streakings as well. You'll also notice near the edges, you'll get this kind of cupping. It'll droop in the middle. These inserts are uniform. So you can kind of see that over spike areas here. You can see the down spikes there, same as beginning too. A little bit of a down spike there. It over spikes and it cups. Well, part of this, the cupping is not just the hardening on the edge. The really high spike there, that's the hardening on the edge. But the general kind of round cupping is making it do this. As you move towards the center, more stuff has been absorbed, so you get less through it, right? So there's just a lower signal when you're trying to reconstruct it, so it tends to just fall down, right? It's kind of an unavoidable thing. You'd have to correct the amount of radiation by location, but then you'd have to know what's there in order to correct it. If you know what's there, why are you imaging it? Right? So it's kind of a catch-22 in that sense. Now you can go in and people will do a very low dose initially, and then they can refine certain areas they care about to go higher in those areas where it's crucial to try to take care of some of these. But it's just important noticing that is a feature. That doesn't mean it was really dense on the outside and its values are coming in now. That's really, it is just consistent. That's an effect that's not true because of the way radiation gets absorbed.
What's the difference between the upper left and upper right? Like, they look, the upper right looks better.
Yes. So this is looking on this particular one, the difference between a straight filter back projection if I do iterative type reconstruction to correct it. Right? It cleans things up. And again, because I'm not relying in all directions equally, and because I don't smear. Filter back projection literally smears it back and then filters it, or filter and then smear back. And you kind of work into it. But like I said, when you deal with other ones like an iterative type reconstruction, I can take a look at different directions and do them. And there's no actual, smearing going on. Each voxel is calculated based off an intersection of hyperplanes. So it doesn't have that same type of an effect. So yeah, the point is there's lots of things that will happen, and you got to realize these are not true things. So realizing what type of things can happen, you can look at them and see. Another one is distortion. What's the difference between a distortion and an artifact, right? Artifact is not really there, right? It looks like it's there, it's not, right? But isn't that a distortion? No, right? I mean, in common parlance, people might say those type of things, but it doesn't mean that to us. If you were to say, what do you think distortion really is? What would you quantify it as?
The image itself appearing not as it is. So whereas an artifact is something else appearing that's not actually there. The distortion shows you what's actually there, but it just appears weird.
Yeah. So there are some artifacts that are that way. So we're going to quantify distortion into one particular area, right? Artifacts will be like the signal itself looks wrong, it's too high, it's too small, it cups across the figure, things of that sort. This is going to be geometrically, it's been altered. So the signal is correct, it's just not in the right place. So when you hear distortion, think it's been physically moved or stretched in some way. Right? Whereas an artifact means the signal itself is not reliable at that place. Right? So we're kind of drawing a distinction between, if you think of it, the X plane and the Y plane, right? X is where it is and Y is what it is, the signal. Right? Distortions are going to be something that change where it's located, your spatial spot. Whereas distortions are going to cause it to appear like there's a signal that's not really there. Does that make sense on the distinction? Okay, there's two types that we worry about, even and uneven. Even is nice, right? Even is things like a cone beam CT, and the x-rays go out in a cone. The further you are away from the cone, it's going to be magnified or shrunk, right? Because the same things, they're moving in basically straight lines. Therefore, if you're further away, you're taking up a smaller piece of the field. That's pretty straightforward, right? But it's really important when you're circling around an object, that object is not a uniform distance because it's not a uniform shape, right? Your head is not the same front to back as it is side to side. Therefore, as it's rotating around you, there is actually some spatial distance that's going on. We have to correct for it, right? If I'm trying to compare two x-rays of you, right, I need to make sure that they're at the same distance or correct for them to see how things have changed over time. Right? So, you know, it's not that that one isn't there, it's just pretty straightforward for how to deal with. The uneven is more of a pain. These two ones here are ones that are kind of more common to deal with. So colonoscopies, right, one of the most common procedures that's out there. In order to be able to check your entire colon when they're looking for cancer, they need a fisheye lens. So that's basically, everybody know what fisheye is? Right? If you haven't, just take a look at GoPro camera footage, right? To be able to capture the whole scene, right, they'll typically use fisheye. What's the advantage to fisheye?
You see more.
Okay, so I see more angles, but why not just make it an even uniform shift? Because it's not uniform and it's shifting.
The lens itself would have to be there.
Yeah, but fisheye, there's a different advantage you really want.
Want to see what's right in front of you better?
Yes. So right in front of you, it's pretty normal, and then it blends off to the side. So it kind of gives you a blend of, I can see what's straight in front of me, nice and fairly undistorted, but the further out you get to the side, the worse it gets, right? But I often only use that to kind of tell, ooh, there's something I need to look at, and then I can pull in my high resolution. So that's what it's usually used for. They're looking for, you know, basically polyps in the colon, and they see something, and then they turn the camera to be able to look at it. But when you're looking at it and trying to figure out how big it is, the size of it is important to be able to tell how frequently you have to recheck, because it tells how fast they're growing, i.e. what's your propensity to generate colon cancer. And colon cancer, timing is really everything. If you catch it early, it's pretty much 100% treatable. Very, very low cases of problems when you catch it early. If you catch it in stage 3 or 4, pretty much a death sentence, right? So it's kind of got this really sharp curve between I can take care of it and I'm sorry, right? You know, and we're trying to always push that, but you know, it's a big difference. So being able to accurately size it tells me how frequently we have to do this. It's expensive, it's uncomfortable, people don't like to comply, so therefore you really want to get that timing right. So being able to correctly scale things is important. Right? Gradient nonlinearity, this is one I've done some work on in the past. I guess I've got some pictures of these too. There's fisheye camera if you haven't seen them before. You can see the central area is pretty straightforward, but see how distorted it gets to the outside. So that kind of shows you that area. The center looks better resolution, basically. With MRIs, we like to think of it as a rectangular coordinate, but it's not. Right? So this is you in the MRI, right? Notice these lines that are going through here, the magnetic field lines, that's what we consider basically our straight lines for where all of your voxels are going. That's what actually builds those voxels physically, is those magnetic field lines. But notice they diverge towards the outside. They're not straight lines. Right? So we do a lot to try to make them as straight as we can, but they're not. So that's a cube. This is some work one of my students did in 2005 to generate a mathematical model to fix this. Right? And this was an image of that. That is super precision. Right? And then we added oil for a very strong signal. We, you know, removed air from it. We did all kinds of crazy stuff. Look at what the image looks like. I can guarantee you that is square to as good as you're going to be able to measure it. Right? We x-rayed it and everything. It is square. Okay? So look at it. That's what the MRI generates. See the curved walls? Right? That's caused by those spherical waves. Now, we can use this, and did, to calculate where those are and move them. We found for this one, this was a 1.5 Tesla machine. Right? So newer ones are around like 10 Tesla. Right? So they're getting stronger and stronger, but you know, that has its own little disadvantages. But when you look at like this situation, things could move up to, worst case scenario on a pixel misplacement, was 2.5 millimeters. might not sound like a lot, but each of those little nodules is 1 millimeter. So you could be off by 2.5, of your voxels inside there. When you're trying to do precision surgeries and that, you're trying to look for margins on cancer, you don't want to be off by that. That's often why people will just take MRI ones and fuse them with x-rays. X-rays have very good spatial qualities, very low distortion. And MRI has really good tissue separation. So that's one way you can do it, but it's, different things, right? So anyway, this is kind of like one of the classic examples of spatial distortion. One last thing just to mention, has everybody, when you went through and dealt with, you're familiar with the whole confusion matrix? We don't do this one all the time, but it is important to tell what it is, right? So does everybody know what it is? We don't have huge amounts of time. So if everybody's like, comfy, I'm cool, right? Some are saying yes, some no. Let me just do a real quick thing, right? So this is the actual truth, right? This is what you tested. So, and you'll break down the numbers. So if your test is the same as what it is, it's a true positive, or a true negative if you don't have it. It's a false negative if the test said it was negative, but you had it. Right? A false positive if the test said you have it, but you don't. Right? Then obviously these have a lot of ramifications on life. So there's a couple different ones. If I look on the test, and this is usually what most people look at, what's the PPV, the positive prediction value, right? Which is basically true positives over the sum of these two items in the column. So if you put the numbers in these ones, if I add these two together, that's the bottom, right? That one over this is how likely, when I get a positive, is it really a positive, right? And the same thing over here, right? Sum of this column, but this one divided by the sum of the column. If I get a negative, how likely is it really a negative? That's what most people look at, right? Is that a good measure? It sounds good, doesn't it? It turns out it's not. Doctors will never use that. Right? The ones that matter are actually these two, sensitivity and specificity. The other column, right? Or the rows on. Right? This is true positives over the sum of these. So this is if I have the condition, I really have it. How likely does it tell me that I have it? Right? And this one is, if I really don't have it, how likely is it going to say I really don't have it? Okay? So this is deciding, this is kind of the a priori situation, right? This is after I've done the test, you're trying to figure out if it's good. This is when should I give the test? Right? So the general thing that doctors use, and this matters because as an engineer you want to design around this idea. So they have a cute little saying, spin and snout. So think spin, right, and a snout. Right. So snout, sensitivity, SN, right? Specificity is for the spin, right? So sensitivity, if the sensitivity is high, snout, you can rule things out. So if the sensitivity is really high, it says you can trust your true positive. It's not likely that the person was negative in that case. Right? So they go snout, right? If this column is really high, I can get a pretty good idea that there's a decent chance you're in the group, which means I can rule you out if you didn't get it. Because the likelihood that you were here, and we're only considering this spot, right? How likely do you have it? We're assuming we're in the positives, right? So if you get a false negative, that's not likely if this number is high, right? So this is good, right, to be able to rule people out. So we use those type of metrics when we're doing screenings. You want to get rid of people who are not likely to be there. Right? Okay. And then there's spin to rule things in, right? So spin, what that means is if the specificity is high, then I count you in the group,
Question.
right? Or sorry,
If
the
your sensitivity is high, does that mean that it's not likely that a negative is false?
right?
So like if you get a negative result,
Yeah, so if the person has the case, right? So you're making the assumption, right? In order, sensitivity is only looking at people who really have it,
okay,
right? So it's saying how likely, is that test result going to reflect that actual condition, right? Is it going to do a good job if you actually have them, right? So what we will usually do, I actually said that this one is the screening one and that one's the final, right? So I use the screening one, right, to determine should I do this one. Because this one, if this is high, right, then this is going to be a high situation. It's negative and I'm going to get a good result, right? So if I were to apply this test, I'm not going to get, a lot of cases. If you get a positive, but you were actually negative, that's going to be low, right? If this is high, Tn over Tn plus Fp, this is low, right? So when I get a positive, right, if I was doing something with a high specificity, right, then I kind of need to do more questions because it's, it wasn't likely you're going to get a negative off of these. If you got the negative, it's, you're highly likely to be in. We're taking a look at the negatives again, right? So if any positive does tick up, I should look more, right? And if my true negatives, like in the ultimate extent, assume this goes to 1, basically, or really darn close to 1. What I'm saying, if you don't have the case, really not likely you're going to be over here, right? So, this is used, in that kind of that spin area that's on. So it's just saying in advance, should I apply to it? And what you're concerned with is, what if you have a very large population and it's a rare disease, right? These ones will allow the population size to skew you, right? So the basic rule is sensitivity, snout, right? You can rule people out, right? And spin, specificity, we count you as in, right? So when we do a test, if it's got a good specificity, right, you're not going to get, a lot of false positives off it. So that means any positive you get, you should look at, right? And you're going to really be sitting mostly in this kind of true negative zone. So that's good to just apply broadly. So if you've ever seen things like in COVID, they had 2 tests, right? What you do for that broad one you apply to everybody is you want to make sure that it's got a really good specificity. So you don't get, a lot of these kind of false positives, right? Because if this is high, you don't get a lot of those. So if you got a positive, we should look at this some more. But then let's check, right? It doesn't tell me whether it's true. It just tells me these were really small, so I'm not going to get a lot of fake hits. So now I can do a more precise test. All right. Does that make sense? Okay. So that's really what we kind of look at. And in any case, we want these. If they're both high, that's awesome, right? But how you pick them is, like I said, spin, right? This is to rule you in, and snout, that one to rule you out. So the acronyms will always help you to kind of figure out what you want off of. When we talk accuracy, that's down here, right? This one just makes people feel good, but it's not really good for predicting or saying which way to go. The other nice way to think is this is the a priori statistics. These are the a posteriori. All right, so before you give a test, which one should I give to get a good result? That's what I want from sensitivity and specificity. Okay, that's end. Okay. So hopefully on MATLAB, we'll see if I can open up just the regular one here. So App Designer, you can also launch, my App Designer is going slow here. If you want to build, this is kind of MATLAB's way to build little application interfaces. Everybody ever used App Designer before? On the command line, you just type App Designer, all one word. It'll launch, hopefully will launch. Hey, there we go. And it basically gives you this interface, right, that allows me to do it. There's two views, design view and code view here. So I'm going to mention this because when you're trying to build your own stuff to test them, I think it's pretty nice to build it within an interface. So you don't have to keep relaunching code all the time. It lets you use it and away you go. So design view lets me just kind of put together the things I want. I can come over here and just drag whatever I want on. Right? So I don't want to do this because it'll mess things up, but it just puts them in here for you, and then I can click on the particular ones. And like, for instance, this is an image, so it gives me lots of different choices that I can set. For the contrast knob, I can set the label, and I can set the label by just clicking on here. Right? I can come in and set the initial spot it's pointing at by value. The limits are 0 to 5. Right? So it just lets me do all that kinds of nice, easy setup really quick. I can drag and drop pretty pictures, right, including little axes and everything else, and put them in. And all I've done is literally just grabbed devices from over here. I grabbed the image, I dragged it over, so on and so forth. And then you just click on them. Like, for instance, right here, the noise one, where I just set the amount of noise you have. I can set the values. And right here with callbacks, I can set them. If it changed at the end of the knob and you release it, that's the change. Changing is you're turning the knob. So if you use changing, it'll slow down your performance, but it lets you dynamically look at it as you're trying to turn. So there's a lot of cases where that kind of makes sense because that's what you want to do, is turn the dumb thing and see what happens. There are some cases, like for instance, picking what type of filter, it makes no sense, right? I'm not halfway between a median and a mean, right? You're one or the other. So I just did those ones as they changed. The second I click on them, I can go to the code view, and this gives me all the code that did it. Let me close this down, right? And it'll make them. And this one isn't showing it quite as pretty. On mine, see how there's these kind of like line breakpoints, right? On my one, on my personal laptop, they shade these out because these are ones you can select them, but it won't let you change them, right? So it should block me from trying to mess on those because that is code it generated. So I should be able to type, and then it should go, you shouldn't change this, right, and stop it. So it only wants you to change inside here. So it lets me just kind of pick in advance, right? Startup function is the one that initially runs. And so this is really where you describe what happens. Now, I ended up adding, I initially was just going to put like one thing and let you change contrast and stuff. And I did, and it was so much fun, I kept adding more stuff. So I probably should have written, like I just copied this code a bunch of times because I was being lazy. I probably should have stuck it in a function and just called it a whole bunch of times with passing different values to it. But, you know, I'd add a knob on this, it's just quicker to paste it. And then I found out I'd added 5 knobs, and I'm like, damn, it would have been better to do the function. But so that's why it's kind of messy on there. But it's actually pretty easy to write. So this is an application. That's the knobs grabbing the value. So it'll literally grab the value of those knobs. Noise will grab the noise knob, or N grabs the noise knob. This noise grabs this little drop down here. You can pick what type of noise you want, you know, Gaussian, Poisson, stuff like that. All right. And then F is what type of filter do you want to apply to what's going on. All right, so that gives you kind of, these are the basic drop down interfaces. And then I just ask, position here is where the image is. So app, image, position. And it'll tell me how far over and up. But more importantly, the next two numbers tell me how big it is. All right, so those are the ones that I really care about. So you'll see like here, position 3. So that's just finding out, in this case, it's height and then width, right? Row first and then column. So position 3 is how many pixels vertically. So that's all I'm doing here is grabbing so that whatever I generate is the right size for here. Yeah, I probably did forget to do this. There was like a big chunk of code here, and it's kind of ugly to just do it. This just makes a box, right? And it just sends back an image that is, we can kind of write the code quick if we want to, but maybe it'll be a fun one for you to try. So it'll give you a little measure. I'll put one up eventually that answers, so I'll go back to my office and put one up. But I'd like you to try it. It shouldn't be too tough. All I did for this box, it's just a simple function, and it makes a matrix. You pass to it, a height and a width, rows and columns, right? So, this is your height, your width, the rows and columns. You pass those two numbers. And it's 1/4 of the height up and down, and 1/2 in the middle is the size of the box, right? And the same thing side to side, right? So it just makes a little box, two different values, right? The contrast is the difference between the foreground and the background. So you'll see two numbers F and B, and it's just the height of this one and the height of that one, right? Now the key thing is when you're doing this for an RGB image, this just returns one gray pane, because we're just going to make it a grayscale image, so we'll just copy it 3 times. But RGB images are unsigned int 8, right? So just do a cast when you do this, right? It's easy enough. So for mine, all I was using was, basically do 0s and 1s, and you can just piece together, right? You have those 4 basic things. And this are identical, and that are identical, and the corners are identical. So you really only have 4 objects, and then you just place them together. But just make sure when you make the, this is B. So I used RepMap. And this actually makes it even easier for the unsigned in. Is everybody familiar with RepMap? It's kind of like 1s and 0s. It's a repeated matrix. It just repeats a pattern inside. But the nice thing about it is you can also specify a type. So unsigned int 8. And then I could say, for instance, whatever the background was. Right? And I just say, however many rows, however many columns. And it'll literally put up the right type and the right size. So that one's 1/4 of whatever the height is, 1/4 of the width. And so I just made those ones and assembled it into one matrix I and passed it back. So it's really a pretty trivial function. Right? But it is good to get used to how you build them. And you do want that unsigned int. Right? All I do for that one after that's all I use, right? So when you look at it, it passes the eye back, and I pass that grayscale version back because when I add the noise, I want the noise to be the same in all 3 planes. And if you pass back a 3-dimensional color image, the noise will be different in the 3 planes, so you'll get this colored noise all over the place. And I just wanted one uniform noise. So I just did it on 1 plane, and then I concatenated them together. So once I made the image, you can see down here, this is the actual one that gets shown on the screen. And it's just, concatenating, right? A 3-dimensional image, here's my 3 eyes. And it just stacks them. And they're identical, so that's red, green, blue. If you want to change them, you can obviously now make full color images by hand. But we just do it gray so that anything we do gets copied to all 3 places and stays consistent. Is that fair? Okay. After that, it's really just play to feel comfy with it. Right? So what I want you to do is try to make that change, and then go home and try. Adjust the contrast, adjust the noise level, try different ones, and try different filters. You'll find mean works really good for some of them. Mode works good for one of them, not as good for others. So all I want you to do is play and find out what type of noises, what filters, how well does it work on the contrast. And that's just kind of a play and get experience. You'll see what the noises look like too. Good? Awesome. If you have problems with any of that, let me know. And like I said, I'll probably wait maybe like tomorrow and upload my gray box one. Just to give you a chance to kind of develop your own code. If you wait till later than tomorrow, don't just take my code, write yours, then you can take a look at what I have. Awesome. Have a lovely day.